Electric pickups can tow well. A properly equipped F-150 Lightning Lariat with its max trailer tow package is rated to tow up to 4,500 kilograms, 10,000 pounds. Our question is not whether it can pull a heavy trailer, it is what happens to the trip once attached. A tow rating is capability under defined conditions, not energy cost per kilometer. That is capability versus endurance.
Welcome to Tech with Receipts.
First, three quantities: torque, power, energy. Then, road load. Why air matters so much. Peak versus continuous power. And one real towing run. Three quantities hide behind towing. Torque twists the wheels, and that creates the forward force at the road that moves the rig. Power is the rate of doing work, how hard the drivetrain must work at a speed or grade. Energy is the total available to keep supplying power. An EV can have torque and enough power to tow confidently, yet consume energy quickly once the trailer changes the job. Every towing trip is a road load problem. The truck accelerates the combined mass. The tires lose energy to rolling resistance. The truck and trailer push air aside. And on a climb, the whole combination gains elevation. One distinction matters. Aerodynamic force rises with the square of speed, while the power needed to overcome it rises with the cube of speed. That does not mean total vehicle energy use follows a cube law. It means speed can greatly change which part of towing matters most. Switch to what range actually cares about: energy per kilometer. Divide power by speed and you get energy per kilometer. Same truck, same trailer. Consider 48 kilometers per hour on level ground. Now speed up to 97. The aerodynamic energy cost per kilometer rises sharply. Hold that same speed, 97, and tilt the road to 6%. Aerodynamics does not disappear. The grade cost is added on top. Now slow to 48 on that same grade. The grade energy per kilometer stays roughly constant while the aerodynamic part falls strongly with speed. Argonne National Laboratory modeled this kind of change. At 48 kilometers per hour on a 6% grade, the towed unit's aerodynamic contribution was under 4% in the model. At highway speed, towing-related aerodynamics could add 44% energy consumption in the fully loaded modeled pickup. Of course, real operating conditions differ from all of this. Manufacturers know the air matters. Ford specifies trailer weight and, by battery and towing configuration, maximum trailer frontal areas of about 6 square meters, 65 square feet. Ford warns that exceeding those limits may significantly reduce towing vehicle performance. If trailer weight were the only thing that mattered for towing, Ford would only give a maximum trailer weight. It would not also need to limit the trailer's frontal area. Extra road load has to be supplied by the truck. Energy leaves the battery. The inverter controls electrical power. The motor turns it into mechanical power. The wheels deliver it to the road. Most extra towing energy does real external work, pushing air, deforming tires, and lifting the rig. Acceleration stores energy in the moving rig. Climbing stores it as elevation. Some can be recovered through braking or descent. Losses inside the battery, inverter, and motor become heat, but heat is a branch, not where most energy goes. A short burst of acceleration and a long mountain climb put different demands on an EV. Peak power is needed only briefly. Continuous power is what the battery, inverter, motor, and cooling system can sustain over time. There is no single bottleneck. Each part can produce losses and heat. In one towing model at about 90 kilometers per hour, researchers found roughly 220 kilowatts of peak demand and 180 kilowatts on average.
Towing at highway speed can demand very high power for a long time, not just for a few seconds of acceleration. As the battery delivers more power, current increases and the voltage can drop slightly under load. The longer high power continues, the more important heat becomes. A production truck can reduce available propulsion power during sustained towing. Motor Trend tested an F-150 Lightning Lariat extended range towing about 3,630 kilograms, or 8,000 pounds, on a roughly 4% climb. It reported 79% state of charge while available power fell from 100% to 62% and to 59% on the return climb. It also reported elevated battery temperature with no motor temperature alert. This suggests the reduction was linked to battery temperature. In simple terms, the truck could still tow, but it reduced available power to protect the system during a long, hard climb. This is one observed truck, one trailer, and one hill, not a verdict on all EV trucks. As a counterpoint, Rivian says its team made multiple 11,000-pound Davis Dam runs over 2 days, with air temperatures topping out around 48 degrees Celsius, and surpassed its targets. One event cannot define every EV truck. When protective limiting happens, it is there to keep the system within safe operating limits. So what could engineers actually do about this? There are two separate levers. 1. Make the trailer slip through the air more easily. 2. Give the trailer its own battery and powered axle, so the trailer helps move itself. In a preliminary test, Pebble tested a powered trailer prototype. At highway speed, the truck's energy use fell from about 44 to 35 kilowatt hours per 100 kilometers with the assist on. Neither lever creates free energy. The powered trailer shares the work. Better aerodynamics reduces the work. Slowing down helps too. From about 105 to 90 kilometers per hour, the aerodynamic part of the energy drops by roughly 28%. The aerodynamic part, not your whole consumption. Tow rating tells you capability. The trip determines endurance.